Hello, everyone. I hope everything is working well and you can hear me. So my name is Matt Bovel. I'm a PhD student here at EPFL. I'm working at the LAMP, so that the lab that builds Scala. We are just next to the Scala Center, and I'm co-supervised by Martin Odersky, that I'm sure you all know. My research interests are centered around what we can qualify as precise types. And so today I will talk about precise types. More specifically, I will talk about singleton types, refinement types, match types, and of course, type level operations. I will give a pretty general presentation. It's not very much research oriented. Instead, it will be completely examples based. I will show practical examples of what we can achieve today and also what will be possible in the future. So even if you already know all these advanced types, maybe this later part can be of interest to you. So here is the table of content. Don't worry, there is one item per slide, so it's not that much. And before diving into the subject, let me zoom out a little bit. So writing software is hard. I'm sure you all know that. It takes time, and even so, all programs that we use every day are full of bugs. Software bugs cost the US economy an estimated $60 billion a year, which is approximately 1% of the gross domestic product. So we lose time, we lose money, and in extreme situations, this can lead to catastrophes like the crash of the Ariane 5 rocket, from which you have a picture here. So how can we help? Or what can help? Well, one of the things that can help are type systems. I'm sure you're all already convinced of that as you are Scala users. As you know, the idea of a type system is to assign a type to each element of a program to make sure that these elements are combined appropriately. So if I want to sum two elements x and y, for example, then I write x plus y. I want to make sure that x and y are numbers. Otherwise, this plus might mean something completely different or even not make sense at all. So types like string, integers, or object types are already quite useful, but these are not enough. When I write a program, sometimes I want some more guarantees. For example, I might be interested in knowing that an object not only is a person, but that the field name of this person has a specific value. So I'm going to give a quick overview of these advanced precise types that we have in Scala that we can already use today. So maybe the first one are literal types. That's types that are inhabited by a single constant that we know at compile time. So for example, here, I can type the literal 3 as the singleton constant type 3. Same for Boolean, same for strings, okay? So if you see types as set, that would be sets with a single element. That's why we call them singletons. Oh, sorry. Okay. So another important type that we have in Scala 3 are path-dependent types. I'm sure you also heard of that. So it's also types that are inhabited by a single element, but it's an element that we don't know yet at compile time. So we know it will be a single element. We know its path. That's why it's called the path-dependent type, but we don't know the value yet. So here, for example, I have two value a and b. I just know it's int. And now to see, I want to give the precise type a.type. Okay? So the only value that has this type is actually a. So that gives me a way to model equality at the type level. Of course, we have subtyping in Scala. So the precise type of a.type, is still a subtype of int. So if I want to assign that to D, to the that has the less precise type int, then I can still assign A. What I cannot do, however, is this, for example. If I say that E has the type A.type, it means that what I put in E should have the same value as A, which is clearly not the case if I try to assign B. So we saw simple examples where we just access one variable that is in scope, but you can also have complete path. That's why it's called path-dependent type. So you can access nested members, such that here, if I have an object foo, and I access the field X, and I access the type, I can make sure this is equal to 3. By the way, if you are not familiar with this notation, you might be interested in this note. So this thing here is a special type for which the compiler generates instances if it can prove that we have subtyping in both directions. So when I write that full expression here will only compile if this is a subtype of the right-hand side and if the right-hand side is a subtype of the left-hand side. Okay. How can I use these path-dependent types? Well, an example would be a function that needs to take two elements that have exactly the same value. I can write it like that. And at compile time, I will be sure that A is equal to B. So if I call with 3 and 3, that will work. If I call with 3 and 4, I will get a compile time error. Okay? Just watching the time. Okay. I want to emphasize something that's completely different as type parameters. If I write the same function with a type parameter t, that does not mean the same thing. It does not mean that I want A to be equal to B. It just means that I want to make sure that there exists a type t that is a supertype of the type of A and a supertype of the type of B. So that means something different. And this code, for example, will compile if I have two constant values, 3 and 4, because the compiler can unify t to int, which is correct. So I repeat last time, path-dependent types give us a notion of equality of values at the type level, which is different from type parameters. We can also use that in return types, of course. So that's how we would define an ID function using dependent type. And we call that a dependent method because the result type depends on the argument, on the precise value of the argument. Another precise type that can be useful, it's the one I was mentioning before with the person example. If I want to know that I have an instance of a class, and that on this particular instance, I have a specific type for a field that I know, I can use a refinement type. So here, I'm saying that V not only is a vec, but also that his field size will have the precise value 2. So size has type 2, because 2 is inhabited by a single value. I can be sure that the value of size will be 2. And the compiler can automatically type check this code. If I create a new vector, it's an anonymous class here, and I define that the field size overrides, implements the size that is here with a precise value 2, then I can type it as this refinement type. And then if I access v.size, I can assign it to a value of type 2. So I know that the type of v.size is 2. Okay, now let's talk about compile time operations. So we talked about precise types, about constant types, but it can also be useful to represent operations at the type level. So let me give you an example. This is in a special package that is called Scala compiletime.ops. And if I import the plus, this plus is an infix type, and it allows me to represent the type of the value of the result of the addition of two other types, here two constant types. And the compiler has special support for it, such that If the left-hand side and the right-hand side are constant types, so such as in this example, this type will be folded to the constant type 4. That's what allows me to assign here 4 to the type 2 plus 2, because internally 2 plus 2 is folded to the type constant type 4. Okay, so how can we use these types? Well, first we will need a last building block, which are match types. And that's what I'm going to show in this printf example. So maybe by looking at something concrete, we will make more sense of these precise types. So here is the goal. We have a printf function. I'm sure you all know that. By the way, this is only for the example. I'm not saying we should forget about f strings in Scala. This is just for the example because the printf function is well known. And so what do I want here? I want to know at compile time that the arguments I will pass to the printf functions have the correct types depending on the string that I pass as the first argument of printf. So here I have a string that will take, that tells me that I will need to display a string and a number. Therefore, if I pass a string and a number, I want this code to compile. However, if I make a mistake and swap the argument, I would like the code to fail. So our case study will be how can we write this printf. More specifically, the question is, well, for S, I know the type will be a string, but how can I type the second parameters here so that I'm sure that I will give the correct types here? So a trick that we will use is called parameter untupling. So as you see in the previous slide, this actually will be several parameters. So here, for example, I have 2 parameters. So how can I compute that at the type level? Well, I can actually, at the type level, generate a tuple, and then the Scala-free compiler will allow me to actually write the call like that without having nested parentheses inside. So more specifically, if I have a function that takes an argument that is a tuple with 2 elements, here 2 ints, normally I should call this function with 2 opening parentheses and 2 closing parentheses. But the Scala-free compiler allows me to just write that, and it will automatically convert. It tells, okay, I don't have to write numbers of parameters. I accept 1 tuple, but you give me 2 parameters, so I will automatically convert to a tuple 2. We will use that to write our printf function. So now we know that we will have an argtype here that will be a type that is a subtype of a tuple. Okay, so now what should I write here? That's the question. So I'm going to show you the code directly and go through it. So here is the answer. What I'm gonna use here is a match type. It's the equivalent of a match expression, but at the type level. And so remember, the argument that I gave to this argtypes type is my printf string. And so here what I do is that I am parsing actually this string. So what you see here is a recursive function, the equivalent of a recursive function at the type level. I will read every character and I will return the tuple type that corresponds to this string. So that's the base case. If my string is empty, the type I should pass to my printf is nothing, just an empty tuple. Otherwise, I read the current character, and if it is this person sign, then I should read the next character. And if this is D, so remember here I am at the type level. So all the things you see here are types. So this is the constant type corresponding to the character D. So if I read that from the string, then I will construct a tuple that where I have an element that has type int. This is the operator to construct a tuple. So I'm saying here that the head of my tuple is an int, and for the following elements, I call myself recursively. Okay? And that's all. I can then use that type so that I pass as the argument the string that is the first argument of printf using this path-dependent type that we just saw. I apply the match type that I defined here, and this will be reduced by the compiler to the precise tuple type of the arguments that I'm expecting for printf. Therefore, if I pass this string with a string and a digit parts inside, then the compiler will only accept to compile if I pass the right arguments. So using the summon notation that we saw before, I can check here that the archetypes of this string is indeed a tuple of string and int. So I have a type that depends on another type and that is computed at compile time. That's why we call that type level programming. And as you see, this is very similar to what I would do at the term level. And by the way, you can check if I try to swap the argument, this code will fail. Okay, that was the introductory example of what is type level programming and what it can be used for. I will show now a related example in the real world. It's a regex library that used exactly the same technique to have strongly typed regexes at compile time. So there is a paper about that written by Olivier Blanvillain. I encourage you to read it. But so basically what it does is that if I have a regex, exactly the same idea from the printf code that we had before, with specific parts, here 3 numbers, then there is a match type that computes the precise types that this extractor here gives me. And so I will be sure that this is a number and also that I passed the right number of arguments here. Okay, and I will see now, we will see another example which is similar, which allows us to strongly type roots. That's the typical thing we would have in an HTTP server, and the inspiration I used here is Scala. So it's a Scala library that is used to write HTTP servers. And as you can see, you define a root using, now you're familiar with that, it's similar to the printf example and to the regex example. The first argument is a string that I want to parse, and then somehow I will be able to get parameters that correspond to the matched part for this root. Unfortunately, in Scala, in these examples, the param that I get is always a string. And if the parameter does not exist, I have a no such element exception at runtime, but not at compile time. So let's try to do something that type checks the element that I get from a root, so the matched part, at compile time. So here I will not re-implement the parsing because we just saw it for printf. We could do something similar here, but instead I will give a tuple directly. I will come back in 1 second to why I'm using 2 stars colon here and not 1 star colon. So let's see the definition of this root. I'm saying that the first part is a constant, it's a user, and then I expect a string value. Then there is again a string post. Then I accept an int value. And given this root, I'm passing a second argument that will do something with the matched username and the matched post ID. And I want to make sure that username is a string because I expect a string value here, and that int value is an int. That post ID isn't int because I expect an int value here. Okay. So the first building block of our system will be this string converter that will be the type of these different parts. So that will be the type of string value and of int value. So this is just a function that we expect here. This is just a function that takes a string and parses it to some value. So I haven't used directly a function type here because it's useful to be able to refer to a converter type directly and not mix it with other function types. And also this allows me to match it at runtime as well. So what is the type of a string converter? Well, it has a convert method that is a method that takes a string and return any value. So in the case of the string value, it should return a string. In the case of the int value, it should return an integer. Then the last building block that we need are precise tuples. So unfortunately, I cannot use a normal tuple here. Why? Because by default, the type parameters of tuple are widened by the compiler. So if I write the tuple 1 to 3, it will actually get the type int, and not the precise type of tuple where the first element is 1, the second element is 2, and the third element is 3. By the way, there should be a colon here. So what can we do? Well, for this example, I just defined a helper function that is this 2 stars colon, and that will construct a tuple, but precisely. So what I say is that I expect as a result type a tuple where the head is the precise type of the argument A using a path-dependent type here, and the same for B. Okay, and this type checks, then no problem. Of course, this is not a satisfactory answer to this problem of precision, and I will come back later to this. Okay, now that we have these building blocks, let's see what the implementation could be. So my class root here, the first parameter is a tuple, and the second one, like we had before, is something that should be a match type that I can apply to the first parameter. So these things I just talked about. You have examples of the int value string converter here that parses a string to an int using the toInt method, and the string converter that just reads a string to a string, so there is nothing to do. This is the ID function. Okay, so now here is the match type. So it's similar to the one you saw before for printf, but now we're iterating through the elements of a tuple. So if my route is empty, then I will not return any parameter. That's the base case. If my route is a tuple, then I will match on the head of this tuple. And there are two different cases. If you look here, there are two different cases. Either my element is a constant string, either it's a string converter that will convert the string to something else. So if it's a string converter, here I'm matching on the parameter of string converter, so that's the return type. Remember, this parameter here is the return type of my parsing function. So I match on this, and so if my string converter returns me a value of type R, well, the head of my tuple here will have type R. And then I call myself recursively. If it's just a constant string, I'm not really interested by this because I don't want to record it. So you see here, it's only these dynamic parts that are matched and that I will use in the function here. So in the case of a constant string, I don't do anything. I just advance to the rest of the tuple by going to the tail that I matched here. And that's enough to have my code type check, so that if I write this code here, then it compiles. Okay. Here we are working only at the type level. So a good question would be, Okay, but can we relate that to something at the term level? And yes, we can. So let's define a function, matchRoute here, that will take actually a precise parts of a URL and that will match it through a route that I defined. And this should return in this case, so that's the same definition that we had before. That should be user here, by the way, and yeah, that should be user here. I want to make sure that this will return string and int. And so I have the definition of the return time depending on this route here. But now I want to write a code and to prove that it will indeed return that. So I could just do an as instance of and not care about types, but that's definitely not what I want. So I'm going to show you that I can actually write this matchRoute code without a single as instance of or a single cast. The important thing here is that I'm saying that matchRoute will return something of type route archetypes, so the match type we defined earlier. And then inside my function, I also have a match, this time at the term level. But I'm writing a match that corresponds exactly to my match type. It has the same structure. So remember the match type that is here. I had the structure where I match on an empty tuple, non-empty tuple, and then is the parameter a string converter or is it a string? And so you see here I have exactly the same parts. And therefore the compiler is able to type that as the match type. And so here I'm actually verifying that my code behaves as I want, that indeed will return a tuple with the expected elements. Okay, if you want to play with the code, by the way, you have all the sources. Oh, well, but you don't have the link to the presentation, but I will send that to the chat or something. Okay, so that was the second element. So here we saw how to play with match types. In the first example, we also used type level operations to match the different parts of a string. I did not emphasize this, but we used this char at length and substring compile time operation from the compile time package so that we could read the elements of a string at the type level. So yeah, we saw compile time operations, path dependent types, and match types. We will continue with this element, but now we will be interested in arithmetic operations. So a common need is to type a list whose size is known at compile time. And as you can imagine, it has a lot of applications for machine learning, for example, to type tensors, but also to verify algorithms that act on lists and on trees. So, as I said, the goal is to keep track of the size of a list in its type, so at compile time. Let's see how we could do that with the building blocks that we have. So what I can do, so vec is a new type that is defined, and I will give it a type parameter length that is a subtype of int, but so it will be more precise than int. And the other parameter is the type of the elements of the vector. So then so for this example, I will not give the implementations, but I will only focus on the types. How can I define the append method in terms of types? Well, the resulting type will still be T or S, actually, that should be S here. And the length will be length plus 1. If I take the tail of my vector, the result type will have length minus 1. I will not go through each method, but what is important then are these two methods. If I want to zip two vec together, I want to make sure that they have the same length. So the vector that I pass here must have the same length as this type parameter here. And the result will also have the same length, but the elements of the return vector will be pairs because I'm zipping. For concatenation, I have another parameter here that is the size of the dat vector. So that can be any size, but the result will be precisely typed as a vector of size length plus dat length. So here you can see some examples, and that's all things that already work today. What does not work today is reasoning about sizes that would not be constant. So, for example, if I know the precise size of a vector is size.type, so size is any int, but I don't know the constant value yet at compile time. And here I'm trying to zip it with itself, but with its tail with an element append at the beginning. So probably you figured out that size minus 1 plus 1 is equal to size. However, the Scala compiler is not able to deduce that today. So you will get an error like that. You will say, well, I found a vector of size minus 1 plus 1 while I was expecting a vector of size. That's problematic. So what we need here is a form of algebraic reasoning so that we can reason about non-constant operands for these arithmetic, type-level arithmetic operation types. By the way, these problems are absolutely not new. So as I said, one application is machine learning project. So I'm not the first one to talk about that. There was a conference at Scala Days a few years ago that was proposing a solution using implicits. Here I will use built-in technologies that are in the compiler, so no need to define my own operations in user space. There are all other projects, for example, this TF.T project that is introduced in the match type papers gives example of how to type tensors using match types and type-level operations. Finally, there was also a conference about type-safe deep learning in Scala, which explores the same ideas, and in addition, tensors that have named dimensions. So now we will come to the new thing. So as I said, what we want is algebraic reasoning for operations with non-constant operands. And that's one of the things I've been working on last year. So what we want is this. We want first to be able to order, oh, that should be a plus, of course, or both should be times. I want to be able to order the operands. Why? Because plus and multiplication of integers is commutative. So I can swap the arguments. And if I order them, then I can compare them. So that process is called normalization because we transform types that would be structurally different to a normal form where we can derive more equivalence between types. Another thing that we want to do is to group operands. So if I have m plus m, for example, I want to know that it's 2 times m. Something we might want to do is distribute. And we made a first prototype where we had distribution, but actually we decided to remove it afterward. Because this is dangerous, this is risky in terms of performance. Because if you start to distribute things like that, then you can get exponentially large types, which is in general something we don't really want in the compiler. Instead, if I just group an order, I'm sure that this normalization will always be linear in the size of the types. So for now, no distribution, but we might add later the ability for the user to invoke distribution manually if it is needed to prove that 2 types are equivalent. An interesting question is when to normalize. So in our first prototype, we were normalizing eagerly, so that if you would create a vector of type m plus n, and I know that m is free, then I would directly normalize such that the type of v would be n dot type plus free. Why? Because m dot type is free. So the normalization process would directly dereference these path-dependent types to their underlying types if they are singletons as well. We decided to not do that in the end, and now we're doing the normalization only lazily when comparing two types if it's absolutely needed. This is good for performance, but this is also good in terms of user experience, probably. Well, I might be interested to have more opinions on that, because that can be misleading. You write a type explicitly here, you write a type parameter explicitly, and you get something that is completely different. So we felt it was not right, and so we decided to keep the types as they are, but only normalize them in the type compare if it's needed, and if we cannot prove that the types are equivalent with any other simple structural comparison. So the machine learning library I was mentioning before, tf.t, has an operation, so it's a wrapper around the TensorFlow Python library that you might be familiar with. And here they are using tuples in a they are using a similar data structure to the tuples we used before, just with this different operator here. And here I'm constructing a tensor of zeros that has dimension x times y. And I want to ensure that if I reshape it, so if I change the value of each dimension, then the multiplication of the values of each dimension will give the same result. And so before, the compiler would not be able to prove that x times y is equal to y times x. With the current prototype that we have, by the way, to make it clear, it's not merged yet, it's a work in progress. With the current prototype that we have, this thing here would compile. I have to speed a little bit, so I will not comment the implementation of tf.t, but you have an example here of the main functions if you're interested. So let me show you now what we can do with this ability to normalize type level operations. It's useful to reason about vectors, of course, where we don't know the precise size at compile time, which is often the case if you read some data sets in machine learning. In general, you will not know the exact size at compile time. But it's also useful, as I was saying before, to check that some operations on lists or on trees are correct. So I'm going to show you here how we could type check that our implementation of a map method on a sized list is correct. And for that, we will need an additional building block than what we had before. So before, we just had a class vec with a type parameter. Here, I will create an enumeration, and I will actually distinguish two cases: the case where the vector is empty and the case where it is not. Thanks to that and to the JDT reasoning capabilities of the Scala compiler, this would be subject for a whole other talk, so I will not go too much in depth here. But what it's used for is to infer the type parameter of a match. So here, I know that if I match a vec that is nil, the first type parameter will be 0. Therefore, if I return 0 here, and that this type parameter is the same as length. So as the result type expects length of vector, and I return a vec nil that has parameter 0 that is equivalent to length, then this code will type check. So that's why I need these two cases here. Okay, but that's not really the part that I want to present here. The part that I want to present is this one. So what am I doing here to map? I'm taking the head of my vector I apply a function that will convert it to an element of type S, and then I prepend it to the tail of my vector, which I also map. So that's the classical algorithm to map the elements of a list in a functional way. So to prove that this is correct, I need a similar reasoning to what we had before, because I have the tail that has size length -1, and then I add something. So the result will have length -1 + 1, and I need this normalization process to prove that this is indeed length. And using our prototype, this type checks. Okay, I will not show that. And yes, maybe I will try to do this part quite quickly in 5 minutes. So we have seen several examples where we use match types, and we have an equivalent at the term level. So we had the example of the route function, match route, and we had the example of the map function. And as you saw in these cases, maybe if I show this one again, for example, we're actually completely duplicating code from the term level to the type level. As I said, to type check, these two structures must be the same. So a question we can ask is, why not infer them? And so that's something else I've been working on. So maybe we could type every match expression with a match type. Why not? We have subtyping in Scala, so this should work. Well, not really. There are 3 problems with such an approach. First, the types are supposed to help you think, and they're supposed to be approximations. So imagine we always have a type that exactly corresponds to the term, then you will have extremely big type, and it will not be that useful. So we want precise types in some cases, but not in others. Performance is always an argument to say, well, we will have bigger types if we have more precise types, so maybe it's not a good idea. And the third thing is that it can actually break backward compatibility. In Scala, you cannot always replace the type of a term with a subtype of this type. It can break something like implicit search, for example. So implicit search is something that is heuristics-based. It's not completely formalized. So yeah, we do not in general give guarantees that an implicit search will always succeed, but we will try, of course, not to break existing code. So that's really something to take into account when trying to type things more precisely. Let me go to the last part. So we have a few ideas that we are investigating in parallel here. The first, the simplest idea for these precise things. Here, remember the example I had for the tuples. I could have just a helper function that is a separate term level construct to type a tuple precisely. I could maybe have the same for type level operations so that I can type them from term level operations. And maybe I could also have the same things for constructors. That's not really satisfactory, and that would not work for match types, because we don't want to, well, we could imagine like a precise match that would be typed precisely, but that's definitely not something very elegant. Another possibility would be to always give the precise types to the terms, but widen them in most of the situations. That's actually already what we do for literal types and for union types, for example, such that in the compiler, the type of an if then else is the union of the left-hand side and the right-hand side, but it is widened afterwards. We could do that. The last solution I would like to propose is a dedicated inference mode, so that we would type things differently by a specific, when a specific keyword is given by the user, such that a precise keyword. And that would be finally less verbose. You could just write precise, and the type of all the operation would get a precise type, such that the return type of this string would be a match type. The type of v1 here would be 1. The type of v2 would be 3. And you would get also a precise type here for v3, because the string would be typed with a match type. That's something we're investigating. It would be quite a big change, so we're not sure we want to introduce that directly. It requires some more thinking. That's different options we are investigating to make these precise types even more useful and more usable. Okay, I think that's the end now. Yeah, I said everything I wanted to say. So thank you very much for your attention. I hope that gave you a glimpse of what we can do with advanced types in Scala today, and I hope you will try this and come up with interesting use cases. We are really interested in hearing about them and to see your experiments. So yeah, thank you very much, and have a nice day and have fun with the other talks. Thank you.
All right. Well, thank you so much for that fantastic talk. And it looks like we have a bunch of questions for you. We'll get through a few of these, and whatever we can answer, hopefully we'll be able to answer at another time. But our first question is, does Scala check for termination in recursive match types?
No. The termination check right now is the stack. So in the formalism, you have a notion of fuel that you decrease each time you call yourself recursively. And in the compiler, that's actually just the stack. So no, we don't have automated checking of termination, but that's definitely on the table. And that's indeed one of the next steps to have more general dependent and refinement types in Scala.
Excellent. All right. Next question. How is the type level plus defined? Does size -1 + 1 not reduce because plus matches on the first element?
Sorry, I didn't. So I can show you the definition of plus, which is actually in the introduction here. Okay, so that's just a type definition, which is upper-bounded by int. And then we have some special compiler support for this with specific support for constants, as I said, and then for non-constant as well. But so I'm not sure I got the question.
Yeah, no worries. We have a lot of questions, but we're actually running low on time. So we'll go ahead and cut it here. But you know, if you could check out the questions and hop in, and we'll deal with those at another time. Thank you so much for your time and your talk today. We really appreciate it, and hope you enjoy your time at ScalaCon.
Thank you very much.
Fire in retro rock.
Roger, Matt. Ready to eject.